Hello everyone, I am Yogesh, and today in this episode we shall be continuing from where we left in our last episodes. In our last episode, while we were dealing with the charges in motion, we discussed about that what exactly happens when I am moving a charge against the repulsion of the charge of same say plus q and plus q. So what happens to the energy that I am imparting or the force that I am giving to the charge to counter that repulsion, that is the Coulombic repulsion. Actually that energy gets stored in the form of the potential energy at that point, and then I say that this is the electrostatic potential of this charge at this point. In order to have a very good and accurate measurement, I say that I will consider some point of observation with respect to infinity. That is, I will say that that the electrostatic potential is 0 at some point, I don't know, over there in the infinity, and then when I am moving that charge from that infinity to my point of desiration, I will see that the difference in the potential energy is nothing but that the force that I have applied over that particular distance. In this episode, we shall be going in quite deeper of this concept. We shall be discussing that what is the potential due to a positive charge and how we can see the same effect in the case of a dipole. Now, before considering this case, let us go for a positive charge which is sitting just alone and no one is in its vicinity, but suddenly a very good friend of his who is also positive is coming to meet him. But since we know from the Coulomb repulsion that the positive charge will repel the other positive charge, his friend is finding it quite hard to meet his friend positive charge, and so to help him out, I came there into action. And what I did is that I simply drew a diagram. I simply said that this is the positive charge, that is the friend, say suppose A, and to meet A, a charge from some infinity or from his home is coming, the charge say B. Now since it is also experiencing some Coulombic repulsion, I have to apply certain force, or I have to apply certain energy. I have to give him certain energy to come closer to his friend A. So in this direction I will apply some force. If I take this point as the point of meeting, say suppose this point is say x, so in order to have this friend B at point x, I have to travel this much distance. So for this much distance I have suppose say the force applied is say F and the distance is say suppose delta x. So this is the energy that I am giving to the friend at who is at point P dash, who will come at certain point x to meet his friend A. Now this is all what I have made a story like thing. Now to have a very simple mathematical interpretation, what I have considered is that the friend A is nothing but the charge plus q. It is I have denoted it by positive q, and in order to simplify my calculation, I said that the friend B that is coming to meet him is a unit charge, that is it is 1 coulomb. So at some intermediate point, that is some point in between the path that I have considered, say P dash, the electrostatic force, because obviously there will be some force either of repulsion, either of attraction. In this case it is of repulsion between the two friends. Do you know what will be the force? Yeah, exactly, you are correct. It will be 1 by 4 pi epsilon naught times the two charges, that is q and 1, divided by the square of the distance between the 2 points. I just missed the unit vector to give the proper direction of in which way the force is being imparted by me. But from our previous discussions, what I know is that if I am moving a point from, say, suppose a point B to a point A, then I am doing some work. Oh, if that is the condition, then I have done a very big mistake. Yes, because I only considered a smaller portion of that, but I wanted to go near to my friend. So what I have to do is, I have to pile up, or I have to sum up all those smaller distances to have that bigger distance that should be covered to meet the plus q charge. So what is the simplest way around there? Okay, let me give you a hint. Do you remember the continuous charge over distribution? We have got certain discrete charges, and in order to have the continuous charge over distribution over a body, what I did was, yeah, exactly, you are awesome because you knew it. I simply had a charge and I said, okay, if this is the distance, I simply integrated it over all the surface. So in the same way, I will say that I have got 2 points of observation, right? One is the infinity, because I don't know from where he is heading, and one is the point at which they are supposed to meet. Say that point is R. So when I integrate the force that is applied by me, or the smaller distance that I covered with certain force, it will give me a very small work that has been done by me. What I will get is that I will simply get the total work done in moving the unit charge, that is the friend B, from an infinite point to a point A near the plus q charge. But here is a catch. In our previous episodes also, we discussed a very good thing. We discussed that if I am doing some work in moving a charge from a point of my interest to the point where I should keep that charge, then that is stored in form of a potential energy. But work is also a form of energy, na? Yeah. So by definition, what we have derived unknowingly is the potential that is present with that charge at point P due to the plus q charge. And so we define the potential as V is equal to q times 1 upon 4 pi epsilon naught r. Oh, so you must be thinking where the 1 by r square went. Well, actually, whenever you will integrate it, the 1 by r square will simply give you 1 by r. So after integrating 1 by r square, what I will get? Yeah, I will get minus 1 by r. Now you must be asking me, oh, from where this minus 1 came? Actually, minus 1 came from, yeah, the integration. But you must be remembering the Coulomb's law, and the Coulomb's law says that if there is a repulsion between two charges, then what is the nature of the force? Yeah, it is a repulsion, but what is the sign of it? Exactly, minus. So the minus from the integration of 1 by r square is minus 1 by r times, since the force is repulsive, I have got minus r. So the minus minus will give me plus, and I will have a very definite quantity with a satisfactory result. V is equal to plus q upon 4 by epsilon naught r. Now here is a catch. If you think that this is only possible for a repulsive case, that is you can only bring a positive charge towards a positive charge or a negative charge towards a negative charge, then I will be really very happy to tell you that you can even take a positive charge and keep a negative charge just near to him, and then you can take that negative charge away from him. So what will happen is that the force will be positive, and the 1 by r square will give you minus 1 by r, but due to the direction vector we will get a minus, and still then the potential will remain positive. Well, I am really tired of only talking about these single charges. I think we should also discuss about a very famous and exciting quantity that we discussed there. Yeah, we should discuss about the dipoles also. Why to leave them? Actually, the dipoles are a very important part whenever we are trying to study the electrostatics or the charges in motion. So suppose I have got a dipole. Say suppose this dipole is at point A and this dipole is at point B. This is the midpoint of the dipole. I say it is X, and this is the point P. It looks like a very strong charge. Yeah. Okay. So what I am going to do right now is, I am having a thought in my mind that if I place a charge here and if I want to move that charge nearer to this dipole, say suppose to the midpoint of it, what will the charge experience? See, since this is positive and this is negative, so it will simply attract it, but this will simply repel it. Now that's why you must be thinking that why I said that the dipole is a very interesting case. Just imagine, in a single case you will encounter two exciting things: repulsion and also attraction. So I am trying to move the charge that is at point P to a certain point X, and if I say that this is not exactly point P, I am moving it from, say, some farther off a distance, say infinity. See, physics is all yours, consider whatever you want to do. So due to this point B plus, there will be a repulsion, and so it will be minus 1 by 4 pi epsilon naught times the q, and since I have taken it as a unit charge, it will be simply 1 by r1. This one will be the negative charge, it will attract it, so the force will be positive. I will have minus sign is gone, and I will have 1 by 4 pi epsilon naught times q by r2, where r1 is the distance between this charge at point B and the point P, and r2 is the distance between this point A and this point P. But here I am seeing something quite different. The distance between the two charges is 2a. So the distance of this point from X is a, and from this point to this A is a. And if I look at them, I will have something very quite familiar which I can do quite easily. I can see that this r1 square is nothing but the square of this r plus the square of this a. It is minus 2ar cos of theta, because there are always a certain angle of inclination and I must take that into consideration. Similarly, if I go for this negative charge, this is r2 square is r square plus square of this distance plus 2ar, that is 2ar cos of theta. Now the very next thing is very easy. You will have to find out r1 square and r2 square in terms of r square, and for that you can take the help of the binomial theorem, which will solve your problem quite easily. And when will you arrive at a particular solution, you will be quite amused to see that the potential due to an electric dipole has got a 1 by r square dependence. But in the case of a single charge, we had 1 by r dependence, right? So why is it happening? Well, in layman language, I can simply say, since there are two charges, they have got their own Coulomb repulsion, they have got their own positive or their negative potential, and when I am doing the binomial expansion on all other things, the 1 by r square term is coming into existence. So what we have discussed so far? Only two cases, quite interesting one. We discussed the potential due to a single charge. We found it out, it had the 1 by r dependence. We also calculated the potential due to a dipole, which has a 1 by r square mode dependence. Well, that's enough for now, but in the coming lecture series, we'll be discussing what is an equipotential surface and what will happen if I don't have one single charge but a system of charges. Thank you.